Hey, in this video, it's part 2. It's a continuation of part 1, where we looked at the correlation between the variate values and the ranks. So the actual values that in a sample, and then the ranks of those values within the sample. And this is pretty big into non-parametrics. We don't use the actual values of our data. We use the ranks of our data. And how well are they correlated? And it seems like a logical question. We do this in linear regression where we have two independent variables and they're highly correlated. We might leave one of them out or use principal components to combine them. But we want to know how correlated things are. And so we derived this formula in part 1, and then I displayed a table in the interest of time and said, if this is the underlying distribution, these are the correlations, or asymptotically, these are the correlations. And I used the R software package and ran simulations, and man, these are right spot on, and it's just so fascinating. But to know the formula, finding the mean of these distributions or the variance is sort of straightforward. This one, actually the logistics of interesting derivation, which I might do actually, maybe my next video. But this one is the tough one in the formula. And so my part 2 is deriving these values for these distributions. And so that is it. So let's jump right in. And again, this is the formula, and the mean and the standard deviation is pretty easy for a given distribution. So we're only going to focus on this. And so for a uniform distribution, the mean is 1/2. The variance is 1/12 actually. And then the CDF, or the cumulative distribution function, is x. So then to find the expected value of this, and so f of x is 1. So here we x times x is x squared, and we're going from 0 to 1. You integrate it, plug it in, we get 1/3, and that's what was on the table earlier. Now for an exponential function, f of x is this exponential lambda equal 1, expected value 1, variance 1. The CDF is 1 minus e to the x. We're not going to derive any of those. So to find the expected value of x, f of x, then we plug it in. So there's x, there's the CDF, and there's the PDF. So then you combine those, and that minus, we can break it apart and do 2 integrals. And then I do integration by parts here, which is this piece, and integration by parts for this piece. And then evaluating this goes to 0, 0, and then we have to evaluate that. This piece, you plug in infinity. This goes to 0 faster than that goes to infinity, so that's 0, and plug in 0, you get 0. And then we have to evaluate that. And then to evaluate it, we integrate it, and we get 1. Here we get minus 1/4. And so the answer is 3/4. And that's what was in the table. So on a normal distribution, this gets a little more complicated. The mean is 0, the variance is 1, and the CDF is, the cumulative, and that's the phi, the PDF of a standard normal. So whatever it is. So now to calculate this expected value, we plug in the value. So there's x, and there's a CDF, and times f of x dx. Now this step here, I used the x times f of x is the same as minus the derivative of f of x. That's a well-known formula. I think in one of my previous videos I derived that, so in this video we're not. So now we use integration by parts. So we let u be this and dv be this. So then the derivative is f of x. The antiderivative, we just get f of x. You plug them in, and then here, plugging in infinity, this goes to 1, that goes to 0. Whole thing goes to 0. Here, plug it in, this is 0, this is 0, it's 0. So then we're just left with this. Now, f of x squared is this right here. So it's the product of 1 over the square root of 2 pi times e to the minus 1/2 x squared, and then you square it, you end up with this. So now, whenever I'm integrating formulas, if I can trick it or manipulate it into looking like another distribution that I know that integrates to 1 over its domain, that's what I try to do. So here, if I multiply by 1/2, divide by 1/2, and then that's what this piece is. So I need a 1/2 minus 1/2 x squared. Then this becomes the variance. So I need a standard deviation here. So I take the square root, but that means I have to multiply by the square root of 1/2, and then I break this into 2 pieces. Well, this right here is a normal distribution, and it integrates to 1, so it goes away, and we're left with this, but then reduces to 1 over 2 square root of pi, and that was in the formula, in the table. Now the logistic distribution, the mean is 0 and the variance is pi squared over 3. And actually I do want to do this, show you this. This one here is pretty interesting because you end up with an infinite series that you have to know what it limits to. Then the PDF is this, and the CDF is this. And again, we're not going to show that. I'll do that in the next video. So the expected value of x, f of x, is this. So you put in x, then this times this, you end up with a cubed. Now, I break this into 2 to go from negative infinity to 0 and then 0 to infinity. Because you have to use different techniques, or you have to manipulate them a little bit differently to get an answer. So I'm going to call this asterisk and this double asterisk, and we're going to look at asterisk first. So we do a U-Substitution, or a substitution I should say. So we're going to let y equal this denominator, and then dy is going to be minus e to the minus x dx. And then for this, if we back solve for x, we get this. So now we plug in these values. The dx is this, and that just becomes y cubed. Now this minus and this minus end up canceling, and we're left with this. Now if we let u equal, we're going to do a integration by parts. We're going to let u equal this, so the derivative is 1 over y minus 1. dv is, the rest. Take the antiderivative, we get this. So then on this page, see if we can keep it in. So we get u times v, and then this is v du. So now this is interesting. If you put in 2, you get 2 minus 1, which is 1. Log of 1 is 0. And then you plug in infinity. Now this goes to infinity and this goes to infinity. But the rate at which this is much slower to infinity than y squared. So this ends up going, this dominates that. And it ends up going to 0. Again, that would use L'Hopital's rule, and you could verify that. So then we're left with this. So this is 0. And then here, there's probably a slick formula, but I didn't know it. So I used partial fractions to come up with this. And then you integrate each piece separately, and you come up with this. So that is the log of y minus 1, log of y, plus 1 over y. It goes from 2 to infinity. Now this I combine to log of y minus 1 over y. I plug in 2, and we get this. And I plug in infinity. Here, that goes to 0. And here, this goes to 1. And the log of 1 is 0. So the answer to this, and so that is, and the log of 1/2, you can move that up to log of 2 to the minus 1 power, bring it out front. So when you multiply it through, you get this. So that's the first piece, the asterisk. Now the double asterisk, this we go from 0 to infinity of this formula here. But I'm going to manipulate this a little bit. In here, if you factor out an e to the minus x from this parenthesis, then you end up with 1 plus e to the x cubed. And out here you get an e to the minus 3x, but then when you take it to the top, you get an e to the 2x. So that's what I did from this step to this step. So these are the same. But here I let y equal this denominator, and then dy is equal to e to the x dx, and x is, you back solve here and you get this. Now one note though, that there's only one e to the x here, and there's 2. So, if we take the 1 over, we get y minus 1 is e to the x. So we end up getting, when we substitute everything back in, this becomes y cubed. And x, of course, is when we back solve. And there's one of these goes here for that, and the other one is y minus 1. So now we're going to split this into 2. So really, if you think about it, this times this. So we can go this times that minus this times 1. And that's what we do, is we break it into 2. So then that y cancels with one of those, and we get y squared. And then we get minus, this original. So then if we call this triangle and double triangle, let's look at triangle first, because this piece we already solved. The limits of integration are different, and we have a negative out here, but it's the same, log of y minus 1 over y cubed. So this next derivation, I'm going to just go pretty quickly, and it reduces to this, and that's follows exactly what we got before, and we end up with 1/4 minus log 2 over 2. Derivations are 100% the same. Limits of integration are different, and then we're carrying along a minus sign. So let's spend a little more time on this triangle. So this is the triangle. So now we let u be this top part. So du, dy, y over 1. This dv be the second part, antiderivative. So it's integration by parts. So this first piece is this times that, which is this. And then the second piece is v du, which is this. Now here, the rate, now this, grows much more slowly than this. So if you look at this, it's a vertical line going up, and this function actually, it tails off. It sort of increasing at a decreasing rate. And so this dominates that when you plug infinity, so it goes to 0. And then when you plug in 2, you get 2 minus 1, and log of 1 is 0. So this drops out. And here we're left with this. And then so I put it into partial fractions. And then we take the antiderivatives of those, and we get log of y minus 1 minus log of y. Limits of integration. This is this formula. And then when you plug in infinity, this goes to 1, So that log of 1 is 0. And then it's minus, you plug in 2, so that's where the minus is. You get 1 over 2, which is 1/2. That can be taken up top, which then just makes that 2. And then the expected value of e to the x for the logistic distribution is asterisk. And then this is double asterisk. We separate it into triangle, double triangle. So this was this piece, this was this piece, and we just calculated, oh, maybe I have it backwards. Triangle is log of 2. So, oh yeah, log of 2. And double triangle is this. Then this, and this cancel to 0, and we're left with 1/2, and that is what was in the table. So with those, you can then plug them into that formula for the covariance and find the covariance of each of these. Well, I hope you liked the video. It was fun deriving these expressions, and please like it if you did, and subscribe so you don't miss the next one. Thanks, bye.